Video covers Griffiths E&M section 6.2.1 bound currents. So in a material that has magnetic alignment, we can go ahead and define the magnetization, so capital M, as the magnetic dipole moment per unit volume. Just like we did with the polarization of a material. Magnetization in general is weak, but not so. So we can still define it in this way. Okay, we can go ahead and say that a single dipole with a dipole moment of little m, we can find the magnetic field or the magnetic vector potential specifically at a particular point by using something from the previous chapter, which is just the magnetic dipole moment crossed with script r hat over script r squared, right, where little m is a single loop. Okay, if I want to know about the whole material, I need to go ahead and integrate over that whole material, and then write this as mu naught over 4 pi integral of capital M crossed with r hat over r squared d tau prime. That's all we really need to do, but this is not in such a convenient form, so we can go ahead and split this integral into two integrals, like we did for the polarization. We can write this as mu naught over 4 pi times j b over r prime script r d tau prime plus mu naught over 4 pi k b script r prime over r dA prime, where now we have two different types of integrals. We have a surface integral on the right, and we have a volume integral on the left. And as long as that surface encloses that volume, we are good to go. Right, but I've introduced JB and KB. What are those? Well, the subscript B stands for bound, just like it did for charges, but now these are bound currents. So J is what we've been describing as a volume current. That is our bound volume current, which is now the curl of my magnetization. Bound volume current. And KB is my bound current, but now it is my bound surface current, which is now the magnetization crossed with n hat, where n hat is the surface perpendicular vector. So if you can figure out, well, you oftentimes, or you'll be able to know m, or if you're not solving for it, you know what the magnetization is, you can then go ahead and figure out what the bound currents are. And if you know what the bound currents are, you can find the magnetic vector potential. And there's the same kind of physical interpretation about what a bound current is, like we did for bound charges. Right? They exist, but they're not actually physically moving. They're just pieces of current that don't cancel out with their neighbors.